All right, I didn't have a calculator at home, so I had to work all this out ahead of time using kind of an online calculator. And so I've got all the work done for this last section. Not really doing it in front of you. I'm just kind of talking through it. The target is to model and evaluate real-life situations using radical function. And we're going to do something else today. We're going to make sure that we can see a trend of what's happening as x goes to infinity. And a tool we use for that is the average rate of change. Average rate of change is very similar to slope. It tells us how our output is increasing or decreasing as x gets larger or smaller. And generally x is going to get larger and the output is going to get larger but at a smaller pace. Alright, and I'll show you this down here. So, with calculators, okay, and if you need, we'll go over how to do cube roots and square roots when we get to this. You should be able to find all of these values. So, for A and B, use a calculator to evaluate the model at the indicated points. Connect the points with a curve to create the graph of the model. Calculate the average rate of change for the first and last intervals and explain what the rate of change represents. So let's do that. Alright. So as we go through, a car with good tires is on a dry road. Alright. The speed in miles per hour from which a car can stop in a given distance in feet is given. S of D equals 90/60. So our input is distance and our output is the speed, right? Let me see if that is correct. Yes. So, and what does it give our speed in here? The speed in miles per hour for which a car can stop at a given distance, okay, is given. So let's use the distances 20, 40, 60, 80, 100. Let's talk about what this means, right? At 20 miles an hour, it takes 42.4 feet, right? Oh no, let's reverse that. It takes 20 feet to stop if you're going 42.4 miles an hour. There we go. If you're going 62 miles an hour, it takes 40 feet to stop. If you're going 76, it takes 60 feet to stop. And it takes 87, it takes 80, and 97, it takes 100. And what we're noticing is as these distance increase at a constant rate, right? And distance would be our x value. Let's write an x right there, right? My output, and I know this is an f of x, this is f of d or s of d. My output is increasing at a slower amount than my input. When you graph those points, you can see that sure enough, this looks like a radical equation. This line is evening out. We can kind of picture this as we go. It's becoming almost a straight line over the course of this as x approaches infinity. Alright, so rate of change is literally slope. Alright, up here I wrote the function of x2. That means the output of the second point minus the output of the first point. You're used to seeing it like this, right? y2 minus y1 over x2 minus x1. Very similar to slope. Alright, so if I do that over the course of 40 to 20, right? These are my inputs. 40 minus 20, this point minus this point. That's the x values. And on top we have the y values, 62 minus 42. I did estimate a little bit. That means for this distance, it takes, right, my slope is 1. So this is change in y, delta y. That means the speed for which I stop is about a minute every foot, all right, between that pace. So from here to here, I can stop at about a minute every foot, all right. That said, when we do the last interval, right, so my x value is 97 minus 87, that's 10, right, and the distance is 20. So when I do that, this my speed, right, it takes, if we look at this, it takes a much longer period of time to stop in terms of distance per speed, all right. So, and we can see this thing evening out here, right here, all right. So the rate from here to here now has a slope of, from here to here is up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2, and my slope has definitely changed. Alright. And I imagine as we go across this, my rate of change will approach 0. Alright. So that's just showing you that the rate of change decreases as we go across. Here, let's look at a couple more. right? This one, all they asked you to do is plug in values. That's all they said. Evaluate the functions for 2, 3, 4, 5, and graph it. So it's just kind of plugging in numbers for your depths, right? This is the water draining from a tank at an average speed, right? Characterized by this function, all right? And you can kind of just go through and fill that out. And that's all it asks you to do, evaluate the function. So that means at 2 feet, it looks like water draining from the tank at an average speed, it's not really draining at all. All right. When it gets to a depth of 3 feet, right, the water is draining in tanks at, well, let's see, it says speed, it's 8 feet per second. At 4 feet, it's draining at 11 feet per second. At 5 feet is 13.9 feet per second. We can kind of imagine that the hole must be above this 2-point value. So if I have a tank right here and water's draining out, all right, perhaps there's a hole at 2 feet, and that's why the water is draining. So the higher it gets, kind of the more water is draining out of this tank. But once I get to 2 feet, nothing's draining at all, right? Because I'm below that water level. Just kind of a picture to talk about that a little bit. When I come down here, all right, now this is saying the velocity of a pretty heavy car, right? 1,400 kilogram car. That's well over a ton. At the end of a 400-meter run is modeled by this function, where v is velocity of the car in kilometers per hour, and p is the power of the engine, all right? So obviously the stronger the engine, right, the higher the velocity. We plugged in some values up here. If I plug in a 0, 0 cubed is 0 times, oh, you know what I did? I got that one wrong, so let's go ahead and plug, I'm going to have to change this a little bit, all right? So if I plug in 0, 0 cubed is 0 times 15.2 is 0. You know what? I'm definitely going to have to change this some. So I'm going to erase this and we'll go through this one more time. All right. And if you plug in 60, and again, I used an online calculator. It wasn't a nice calculator, but if I plug in 60, take the cube root of that and multiply by 15.2, we can see that my change over the first 60, I go up 59. Over the next 60, I only go up 16. Over the next 60, I only go up 10. So my rate of change is, once again, following this graph, I'm leveling off. And I really need to put that 0, 0 on here and even show a much greater decline right there. So, and then it asks for us to get the rate of change. This is probably a good thing to erase and show you what rate of change is. So I'm going to write the whole thing here. So that is this. That is the f of 60, right, minus the function of 0. Those are the outputs over the inputs. 60 minus 0. All right. So it looks like f of 60, well, that's 59, minus f of 0 is 0. Those are my outputs that we see here. All right. And then I got 60 minus 0, and that's roughly 1. I'm going to say roughly equivalent to 1. All right. So when you have from here to here, I'm gaining at about, what does this represent? Velocity in kilometers per hour. A kilometer per hour every kind of unit of power that we have. And then you can see as I go to 60 to 120, right? My velocity doesn't increase as much as my power. So there seems to be a situation where, and we see that quite often, right? You get these huge engines, but you've kind of reached that point where a larger engine doesn't make the car go all that much faster. And that's at the very end, we got this huge engine and very little change in these last little bits. There's not much speed given in terms of miles per hour, kilometers per hour from upgrading that engine one more time. And that's all that is. It says use the function to find the velocity where P is 100 horsepower. You just plug 100 horsepower into here and you get, you know what? It's about 24. All right. So again, we're 24 kilometers per hour, right, at the end of a 400-meter run when you have 100 horsepower. Well, there you go. This is it. We will talk over this a little bit more tomorrow, but I'm going to pause this. Sorry that we couldn't do it in kind of in a live with a calculator, but we'll do anything you need in class tomorrow, and talk to you guys soon.